We continue our discussion how we build the proper rules to estimate the unknown parameters. And so yesterday we established two methods, method of moments, method of maximum likelihood. As I said, method of moments is the oldest method, quite simple approach. On the other hand, method of maximum likelihood is more versatile. It has more applications in statistics and econometrics, and well, we are gonna see this method of maximum likelihood many times throughout this course. Well, we know that these estimators are the special types of statistics. They are random variables by their nature, and they must have some sampling distribution. So don't confuse this. Please keep in mind that a population parameter is a constant. I mean, yeah, yesterday I asked you about whether it's possible that this population parameter would change. But even if the population parameter changes, it changes in the predictable way. So you may say, well, on Monday, lambda is 15. On Tuesday, lambda is 14. On Wednesday, lambda is, let's say, 20. So there is a predictable model how this population parameter changes. And still, this population parameter, given the conditions that we estimate this population parameter, is constant. On the particular day, for example, it's constant. But the statistic, the way how we, so you can think about this as the following. So assume that you are playing darts, you know, the dart board. So there is like the circle. In the center you have a target, and then you throw these darts into the target. So the target is always pinned to the same place. So this is your population parameter, the target. But the way how you throw your darts to the target are estimators. And if you throw one dart and you got into the dartboard, it doesn't mean that you are exactly in the center. You can shoot slightly left, slightly right. You can completely miss the target. So that's what we are doing. The problem for us is that this target is hidden from us. So we don't see the target. We are doing this kind of blindly. And we want to establish such an approach, such a rule, that even though that we are doing this blindly, we hope that our shoots are as close as possible to this hidden unknown target. That's probably the best way how to explain what we are doing here for the fifth lecture. Right? So we are blindly shooting some target. We don't know this target, but we hope that our approach is correct. Well, you know, there are some blind soccer players, for example. I don't know how blind people can play soccer, but they somehow are able to do this. And we are doing something similar. We are trying to blindly shoot into some target, and for doing this, we want to develop some rules how exactly we should do this in order to make as close as possible our shoots to this target. Vlad, you wanted to ask something?
Yes, I just don't understand if we don't know where, if the target is unknown, how can we even estimate like where to shoot?
But that's what we are doing. So we are building all these things, all these tools, in order to understand, well, if I do everything properly, then there is a high chance that I'm somewhere around. I'm doing everything correct, and I'm shooting close to my target, even though I don't know what is this true target. That's a problem, and that's a problem of statistics. So statistic doesn't make some unreasonable things, as many people think that statistics just collect the data and publish some numbers and that's it. No. So the real problem of statistics is like this. We want to establish all these things, and actually we already made several things. Look, even though if I don't know the true target, so that was in the lecture number 2, we established a very powerful thing. Even though if I don't know the target, but if I collect a large sample, it doesn't mean that I shoot many times. No, like for the example of shooting is not very applicable. So like one shot, but if the sample size is large, so my shot becomes more and more precise. You see that, like, I'm going closer and closer to the target, even though I don't know what is the target. But I know that if the sample size is large, I'm gonna be, with a high probability, I'm gonna be very close to this target. It's like, you can think about this as a distance from your target. Like if the distance is large, in our case, if the sample size is small, then your precision is gonna be poor. But the sample size increases means that you are making steps closer and closer to the target, like this, and you are about to, just take your hand and put the dart to the target. That's it. And we also know that the distribution of our shots is gonna narrow down as we come closer. Again, so coming closer means that when we collect a large enough sample size. So the large sample means that we are making steps towards our goal, and we are very close to this goal. We are very close to this target. And of course, if you are close to the target, even though if you don't see this target, there are high chances to put your dart to the correct place. That's one story. And another story is about the ways how we do this, kind of how we throw our darts. So those are estimators. The rule how I exactly need to send my bullet or the dart to the target. If I send this correctly, if I do all the steps correctly, playing darts is not that simple, right? Because there are some tricks. You need to make it not straightforward. You need to make some circling movements, and it must kind of go in this direction, like spiral, something like this. If you have a rule how exactly you must make your shots, then once again you can at least hope that since you did everything correct, your result is also very close to your target. But once again, Vlad, you're totally correct. We never know what is our target, and we never can be 100% sure that we are there. There is always some uncertainty. There is always some kind of some idea that, well, maybe we are far from the target, and we never can believe this calculation with full certainty. That's true. That's why we need to know probability, and we need to establish this probabilistic language. And in econometrics, there is going to be even worse thing. Okay, so we want to know the sampling distributions. We want to know how far may be our shots from the target, whether we are very precise and the deviation of our shots from the target is not that large, or our precision is poor and the possible deviation is huge. So at least we know one result. At least we know one result from here is about the variance of our shots. So the variance of our shots depends on the variance of the population, depends on the population variance and decreases with the sample size. So it decreases with our when we go closer to the target. Yeah, and as we know, there are different rules for the estimation. So there are different estimators for one single population parameter. And we want to select the best, kind of the best, but we need to know what is the best before selecting the best. That's a goal for this lecture. We want to establish some properties of these point estimators, and we want to find out how to select from different estimators which one is better. So for example, yesterday we came to the result that method of moments estimator for variance looks differently from the sample variance that we introduced in our previous lectures. And both sample variance and this method of moments estimator are estimators for the population variance, but they are calculated differently. So the question is which one is correct, or which one is better, let's say. Not correct, both are correct, because both are derived somehow. So which one is the better? Okay, so first of all, as usual, I realized that every lecture we need to remember something from the past lectures. So therefore, some repetition. So remember that for any random variable, we have an expected value, which is the first moment around origin. We also call this population mean. Those are synonyms. Expected value, population mean, same. And variance might be represented in one of two possible ways. So both are equivalent. I mean, in one of the lectures, in probability lecture number 7, I derived this expression with the help of this expression. There are like 3 or 4 steps how from here you can come to here. That must be familiar to you. Just not be confused. Remember that we have this relationship. Well, yes, we can denote variance as var. We can denote variance of x as sigma squared. Both ways are equivalent. Now, in the very first lecture, we established that for the sample mean, the expectation of a sample mean is the population mean, right? So the expected value of a sample mean is mu. So what does this mean? If you take the example of shooting darts, it means that when I shoot darts, I expect that my correct steps will lead to exactly shooting the bullseye, so exactly shooting the center of my target. It doesn't mean that I actually will get it, but I expect, if everything is correct, I expect that the center of my potential distribution of my shoots is gonna coincide with my target, with what I'm looking for. So, and the variance is related to the population variance in the following way. It's sigma squared over n. So we also derived this result in the first lecture. Nothing wrong. But now I want to draw your attention to the following. So how I can, by analogy, with this variance, how I can rewrite this variance. So if here was the variance of x, and I took x minus mu squared, and then I calculated the expectation of this expression. So now I'm looking for the variance of x bar, which means that it's going to be x bar minus mu squared. Again, it is not calculated, it is derived with the help of integrals, so with the help of probability mass function. So don't think that this is somehow numerically calculated from the data. And or using this formula, we can plug here x bar squared, which is kind of the average of x squared, right? The average of x squared minus population mean squared. So we would need this thing in a while. So don't be confused. I know from my experience that sometimes it's confused why here we have, sometimes it's confusing why here we have x, why here we have x bar. These two are different random variables. So this is a single random variable, if you want. And this is the function of a random sample, right? So there is x1 plus x2 plus x blah, 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 plus xn divided by n. So this is the function of single random variables. Now, we need to remember about the population moments and their sample analogs. Just yesterday we spoke about them. So the population moments, for example, the first moment, and the analog is the sample mean. Second moment, expectation of x squared, and the sample analog is here. Okay, one additional thing that we need to remember, and this is something new, but the logic is must be familiar. In lecture number 2, we established the weak law of large numbers. So there is some special version of this weak law of large numbers that says that, well, what was the weak law of large numbers originally? Originally, we said that, where is this lecture number 2, right? It was here. Yeah, originally, the weak law of large numbers said that when the sample size increases, the sample mean converges in probability to the population mean. So what does this mean, converges in probability? That the probability that the sample mean will deviate from the population mean by some small fraction tends to 0. Right? So, and so the illustration was given here, exactly with this graph. So as I increase the sample size, the deviation of my sample mean from the population mean shrinks, and as I increase the sample size more and more and more, this deviation shrinks more and more. So which means that the probability that the deviation will be larger than some number, the probability of this is going to be 0. So it was about the population and sample mean, but in general, we can claim that any sample moment, second, third, fourth sample moment, converges in probability to the corresponding population moment. So second moment converges in probability to the second population moment, third sample moment converges to the third sample moment converges to the third population moment, and so on. Just sample mean is the particular case of this, because sample mean is the first population moment. Well, basically this, for example, sample moment converges to this as the sample size increases. It will help us today. And also we established several properties of this conversion probability. So given that two variables conversion probability to the respective numbers x and y, there are some conversion probability to the sum of x and y. If x converges to the probability, if this random variable converges in probability to some x, then and A is a constant, then just the product of this sequence conversion probability to the product of A and X. The same if you impose some function here. So you will see the examples today, how we use these properties. And the fourth is when basically it's similar to the first one, but when we have a product of X and Y, then their product conversion probability to XY. So maybe now it seems something abstract. As I said, today we will use these properties to prove something. Okay, so that was a repetition. So repetition of the variance computation, repetition about population sample moments, and repetition about the closure of large numbers and properties of conversion probability. Any questions here?
I guess not yet.
Not
Okay,
yet.
so you know that everything here is on purpose, so that's why in the subsequent slides you will see the use of all of these things. So first of all, the first property of a point estimator is called unbiasedness. Well, the definition reads as follows. So the first part is familiar. We have a random sample from x1 to xn. Every variable in the sample has the same density or mass function depending on the nature. Continuous variable has density function. Discrete variable has the mass function. We have an unknown parameter theta, and theta has, well, theta belongs to some set omega. Well, theta hat is an estimator. That's what we did yesterday. Estimator is the function of a sample. And we say that theta hat is an unbiased estimator of theta if expectation of this estimator, because estimator is a random variable, theta is a number, theta is a constant. So the expectation of this random variable equals to the true population parameter, to the unknown parameter. If this equality doesn't hold, then theta hat is called biased estimator, and we will hear about bias almost every class since now, especially in econometrics, because for econometrics it's a large problem, the biased estimators.
Is it like dependent?
No. Biased means that, look, I will show you in the next slide. I hope you will understand. It's not dependent. No. It doesn't mean that they depend. It means that, well, when you shoot your target, you expect to shoot not in the center, but somewhere else. So your expectation that you are shooting somewhere, so the center of kind of your expectation is shifted or moved from the center. So the illustration is on the next slide. You will see this. So the bias is, oops, what's here? Yeah, the bias is the difference between this expectation and theta. So I must correct this. Yeah, so the bias is the difference between what you expect and your target. So the expectation and the unknown parameter. So now here is an illustration. Look. So the population parameter is a constant. It is located somewhere. And here the blue line is the distribution of your estimator. So you remember we discussed this several times that when you take another sample, the value of your estimator might be different. But if the distribution of these possible outcomes when you estimate the unknown parameter is centered around the unknown parameter, that there is no bias, which means that when you shoot, kind of you point exactly into the in the direction of your target. You point exactly there. You may miss a little bit, but still kind of you point exactly at the target. Well, when there is a bias, look what happens. When there is a bias, the following happens. You see that your target and the place where you should deviate from each other. So your target is here. You want to shoot in this direction, but the center of your shots is to the right. So kind of you point your dart or your shotgun slightly to the right from your target. And therefore you will definitely, well, in some cases you will shoot exactly there, right? Because it's possible to shoot here. You have a random variable as the estimator. But the center of a distribution of your shoots is gonna be to the right from the target. And this is called a positive bias. And on the other hand, we might have a negative bias when your target is located here, but you shoot slightly to the left from your target. And again, so because of the randomness of your shoots, it might be possible that you will shoot exactly here, but most probably or most likely that you will shoot to the left from it, because the expectation of the estimator is to the left. So now it's not a dependency, no. It's just, it means that the rule how exactly we want to shoot is not perfect when there is a bias. If there is no bias, it means that we are shooting exactly in the direction of our target. But once again, as I said, well, some deviations are possible. So now there are Olympic Games starting. So, and probably some of people are gonna watch biathlon. And you see that, well, there is some target, which is just a big circle. And the sportsmen never shoot exactly in the center, right? So for them to shoot this goal, it's okay to deviate slightly from the center of this circle, right? So the deviation is possible, but still they must shoot exactly, they must point exactly here, exactly in the center of their target. But if they shoot to the right, well, it's possible that they will shoot a target, but most likely that they will miss. And the same here. If they shoot to the left from the target, well, it's possible that due to the wind or, well, some other chances, they will hit their goal, but most likely that they will miss. Well, I hope that with the help of Olympic Games, I was able to explain you what is the bias and why the bias is unwanted property of an estimator. Right? Is this clear? What is bias?
Bias is bad.
Yes.
Nice, bias is bad. Yes, I agree totally. Or at least if there is a bias, you must be aware about it and you must make some correction on this bias. That's also possible. Okay, nice. Let's see on the example. So from the previous example, we found that the way how we should find or estimate the lambda, the parameter for Poisson distribution, is just to calculate a sample mean. So now let's see whether it's unbiased estimator or not. So how should we prove this? How should we prove that our actions are correct? Well, first of all, we believe that the underlying variable x has a Poisson distribution and expected value is lambda. So this is a property of a Poisson distribution. So the next, we want to calculate, look, expected value of our estimator, expected value of lambda hat of this. What is this? Instead of lambda hat, I plug here the way how I calculated this one. Then, well, I hope you remember I didn't put this in the beginning of the slides, but we did it in the first lecture. And in the first lecture, we derived the expectation of a sample mean. It was here, right? So the same things applied here. I first take the constant out of the expectation sign here. I have an expectation of the sum of random variables. Now the expectation of the sum of random variables equals to the sum of their expectations. So kind of the expectation goes inside the summation sign. Now, what is the expectation of xi? It's here, it's lambda. So I have the sum of n lambdas divided by n. What is the result? Lambda. That's a simple way to prove that our rule to estimate lambda based on the method of moments is unbiased. So the best I can expect from my approach is lambda. So lambda hat by method of moments is an unbiased estimator for lambda. So what does this mean? Let me show you probably the illustration of this. So remember yesterday I showed you how exactly I built that example, and we had the following results. Yeah, okay, we had the following result, and then when we calculated the mean of this value, we calculated this 14.98, which was the estimate of lambda hat by method of moments. Well, maximum likelihood gives us the same result. So maximum likelihood is the same. So now look, if I draw another sample, and then I calculate mean, look, now I have another shot, right? And with another shot, I get another result, 15.0. Okay, nice. When I continue doing this, the third shot gives me 15.002, right? So the fourth shot, well, 1498, almost. And so on. So you see, I keep shooting in the direction of my target. And well, my results are always different because the sample is different. So these results are kind of, they are concentrated around some number. I guess you can guess this number. What is the center? Well, we don't know. I mean, in practice, we don't know what is the center, but well, it kind of, it suggests us that the center is somewhere like 15, right? Because the results are appearing exactly around 15. So 0.02 to the right, 0.02 to the left, and somewhere in the middle of that. Well, there is some chance, I don't know, maybe there's 1,000 sample. There is some chance to get something, something not reasonable. I don't know which exact sample will give us okay, so here you see that it's very small number now, 1497. But which sample will give us? Well, we don't know. So here you see 15.0, almost 6, which is kind of huge. But that's the illustration of what we are doing. So when we shoot, we expect that we will point our shotgun exactly in the direction of target. What is going to be the outcome? Whether it will deviate slightly to the left, slightly to the right. Well, it's possible because the action is random. It's based on the random sample. But still we want our shotgun to be directed exactly in the center of our target. That's what happens. And that's exactly what was here when I was showing you in this lecture number 2, when I was showing you what happens to the sample mean when the sample size increases. We knew, so I simulated these random samples, of course, and I knew that the true population mean is 10, and you see that 10 is exactly in the middle of this distribution, but just when the sample size increases, the deviation shrinks, the deviation of my possible shots, but the center is always there, which means that the sample mean is unbiased estimator for the population mean. And here we proved that lambda hat, derived with the help of method of moments, derived with the help of maximum likelihood, is also the unbiased estimator for lambda. So now let's see what is biased estimator. So remember that in the previous lecture we derived that for the normally distributed random variable x, sigma squared hat of, which is the estimator for variance, is this. Now let's show that this is a biased estimator for sigma squared. Well, we want to calculate the expectation. We want to derive the expectation for this random variable. Now plug the formula, how exactly we calculate it. So here we have n random variables and here we have n random variables. So what's this? This is the sample mean, right? This is 1 over n multiplied by the sum of random variables. This is the sample mean squared. So let's rewrite this. First step, sample mean squared. So now, so this now next step comes from the repetition. So what is ex squared? You remember, this is the second moment for x bar, right? This is the second moment for x bar, and therefore I can rewrite it in this way. So let me show you. In the repetition we have this formula here. So look, expectation of x bar squared minus mu squared gives me the variance of x squared. But now I rewrite this with respect to x bar squared, which gives me sigma squared over n plus mu squared. Right, so I have it here, but with minus, because I need to subtract it from here. With the first term, I do exactly the same procedure as for the sample mean on the previous slide. I take 1 over n out of this out of the expectation sign, and then expectation of the sum of xi squares is just the sum of expectations of xi squares. here. Now, what is this? This is the second moment for xi, expectation of x squared I. What is this second moment of xi? We also wrote it there. So there is variance equals this ex squared minus mu squared, right? So therefore, this second moment is sigma squared plus mu, which I write here. Now I have this, I have this, these are constants, these are constants, so everything seems to be very simple. So n sigma squared divided by n gives me just sigma squared, and mu squared divided by n gives me mu squared. And here we are, mu squared minus mu squared gives us 0, but this term does not disappear to get sigma squared, because in the end, I want to see sigma squared here. But the second term doesn't disappear. And this is what? So remember 2 slides ago, the deviation from our target when we calculate the expectation, and then this expectation is deviated to the left from the target. How do we call this?
Variance.
It's bias. It's bias.
Oh, bias.
Expectation does not coincide with the target, with the population parameter. And this difference is bias. So therefore,
I have a question.
Uh-huh.
We multiply by 1 over n, and where does it go? Like 1
Look,
over n
there is
multiplied by...
the sum of these things. So sum n times, you need to sum sigma squared and mu squared, which is what? So sigma squared plus sigma squared plus sigma squared plus sigma squared, and n times. That's gonna be n times sigma squared. Correct? And then you
Yes.
divide this by n, and then you have sigma squared.
Oh, I see,
Okay.
I see. Yes.
The same with mu squared. So mu squared plus mu squared plus mu squared n times. And then you divide this by n, and you have mu squared. So this is the same. So this is the same as here. Look, when you sum n times mu and then divide by n, you have just mu. The same story here. Okay, so what we see? We see that this way of a variance estimation is not good because it is biased. We know what is the bias. We know the size of this bias. It always will shoot slightly left. Kind of your shotgun is not properly calibrated, if you want. So you never point your shotgun exactly in the direction of your target. Your point is always to the left. That's a bias. Well, if we slightly rework this, it will help us a bit later. Well, if I take sigma squared out of the brackets, factor this out, and then here I will write it like this, n minus 1 over n times sigma squared. Well, as I said, this is the bias of our estimator, and this is just a nice result to show what is the expectation of this biased estimator. It shows that always this expectation is gonna be less by the target by this fraction. Now, if you remember both method of moments and maximum likelihood, well, we haven't derived maximum likelihood estimator of variance, but well, you may trust me that both give you the same result. both give you this estimator of a variance, are biased. So this and this are equivalent, just in case. Now, we know that the expectation of this is derived in the following way. What about the sample variance? The sample variance is different to the population, the sample variance is different to this method of moments and maximum likelihood estimator by this denominator. Here we divide by n minus 1, and here we divide by n. So what about this sample variance? Is this biased or not? Let's see. So the expectation of this s squared is the expectation of this expression. So now I do one trick. I multiply and divide by n, like this. So n here and n here. So basically, this is equivalent, right? Now, I know what to do with this, because this is the expectation of this thing, and I know what's that. I know that that this expression, expectation of all the things, is here. I can simply rewrite it, right? So the expectation of sigma squared hat, and then I know what is this expectation. And look what happens. It's sigma squared. So the sample variance, when we divide by n minus 1, is unbiased estimator of the population variance. So now our shotgun is pointed exactly in the direction of our population parameter. That is why when we work with samples, we use this sample variance. We divide by n minus 1 and never divide by n. Because this rule to estimate unknown variance is better than this rule. And better in this case means that we do not produce a bias in our estimates. Well, you will have several examples for your own, let's say, exercises on Wednesday. So you will try to derive the biasedness or unbiasedness of several other estimators. But this is the way how we can. So what Vlad asked me in the beginning. So how do we know that we are shooting in the right direction if we don't know the unknown parameter? And now we are closer and closer to the answer. Because if we develop our rules, so how we should act, how we should behave in a very proper way, and we properly prove all our rules, then with the help of these rules, we can be more and more certain that we are looking in the direction of this unknown parameter, even though we are kind of blind. But if the target is here, at least we are not turned away from the target, but we kind of somehow, you see, we are pointed in the direction of our target, in this direction, and not like 180 degrees from it. And these rules help us to understand that we are doing everything properly. So the next property of a point estimator is called consistency. So this is something different. People sometimes confuse unbiasedness and consistency, but this is different. Let's see how they are different. So the first part of the definition is the same. We have a random sample, we have a known parameter of PDF or PMF, and this parameter must be specified by a set of possible values. We have an estimator, sigma theta squared, theta hat, the estimator of theta. And we say that theta hat is a consistent estimator if theta hat converges in probability to theta. So what does this mean, converges in probability? As the sample size increases, the result, look, there is no such a thing as an expectation or something. The result, the exact shot, not the center of my distribution, but the exact shot, will deviate from my target by infinitely small amount. That's an idea of a consistent estimator. So let me probably also demonstrate you with the help of a previous example. Look, our sample size was 28,800. What if I make it smaller? What if I take not the full day, like 8 hours of trading, but only 1 hour? And inside 1 hour, I will also collect the number of transactions occurring every second, but only within 1 hour. So 1 hour will produce me 3,600 observations, right? So 60 minutes times 60 seconds. So in 1 hour, my sample size is going to be this. So let's see how precise are going to be my estimates right now. Let me put it here. Look, now where am I shooting? 1489. It's, if you remember the results from the sample size of 8 hours, you remember that it was highly unlikely to get such a number because everything was concentrated like 14.98, 15.02, so 200 from 15. Now it's 1489. Well, okay. Another sample, 1488. Another sample, 15. Okay. So here we shoot exactly where we wanted. So let's take another sample. Wow, 1484. So the spread of our possible shoots became larger. And if I take, for example, instead of, what was there? 28,800, right? So if instead of 28,800, I will take 2 days of observations, like multiply by 2. So let's see how precise are going to be my estimates in this case. Look, 1499, 1497, 1501. So you see that the spread of the deviation of my shoots became less and less. Right? So that's an idea of a convergence and probability. There is still some possible deviation and the center is still around 15, but the deviation shrinks dramatically. The deviation from this target. And that's what has been also shown in the lecture number 2 when we spoke about about convergence and probability. So you may want to revise this lecture once again to see what happens if the sample size increases. See, when I take a larger and larger sample, so the probability that I will deviate far away from the center goes to 0. This is about consistency. So, and we want an estimator to be consistent as well, not only unbiased, but also consistent. And there is some relationship between unbiasedness and consistency, but don't take it wrong. So if there is an unbiased estimator, if there is an unbiased estimator. Then this estimator consistent if the variance of this estimators shrinks to 0 when n goes to infinity. But only under this condition. If we have unbiased estimator, it will be consistent when variance of this estimator goes to 0. So we know, for example, what is the variance of sample mean. Variance of sample mean is sigma squared over n. And as n goes to infinity, this variance goes to 0. Therefore, sample mean is a consistent estimator for the population mean. So let's see this. So we know the estimator, the method of moments estimator for lambda. This is just a sample mean. And now we want to show that this is a consistent estimator for lambda. Well, the weak law of large numbers says that the sample mean converges in probability to the population mean. Well, I know that lambda hat equals to the sample mean. And I know that sample mean converges in probability to the population mean. And I know that the population mean in the Poisson distribution equals to lambda. So now if x bar converges to mu, and this is x bar, and this is my mu, lambda, so we get that. Oops. Where is that? Well, yeah, so there is another typo. It must be not equal, but it must be converges in probability. It must be this arrow. Lambda hat, estimated with the help of method of moments, converges in probability to lambda. It's not equal. No, it's not equal. It must be like this. Let me also correct it. So we know that what we have done on the previous lecture is unbiased and consistent. Now let's see another example. Variance estimator. So we know that method of moments estimator for variance, which looks like this. I rewrote this second term in a slightly better way, just x bar, but you remember that it was already shown on the previous example. So now let's see that this is a consistent estimator for sigma. Still, it's biased. It is biased estimator, but it is consistent. As the sample size increases, well, the estimator becomes closer to the population parameter. So now, in order to show this consistency, we need to remember those properties from the beginning. So these properties. First of all, this weak law of large numbers, and second, all these things. So let's see how this works. So the first step. So this is what? This is the second sample moment. This first term. We know that as n goes to infinity, the second sample moment converges in probability to the population second moment, this one, or mu prime 2 is the same. Right, so this is why I showed you this extended version of weak law of large numbers in the beginning, because we needed that version of weak law of large numbers here to prove that this part converges in probability to the second moment. So now the second step. What is this? We know that x bar, as n goes to infinity, we know that x bar converges to mu. Right, so we showed it here. This is just a usual version of a weak law of large numbers. If I increase the sample size, sample mean converges in probability to the population mean. But now I have sample mean squared. What happens to the sample mean squared as the sample size increase? And here, I need this. Property number 3. Look, if I know that sample mean converges to mu, and I apply a function g, in this case, this function g is squared, so then my sample mean squared will converge to what? To mu squared. Right? That's what I write as a second step here. I know that x bar converges to mu, and I know that property number 3. That if I apply some function to my random variable, then this random variable will converge to the same function of the limiting variable, in this case mu squared. So I know that this converges to e of x squared. I know that this converges to mu squared. Now I know that there is a property number 1. So what is the property number 1? Well, if one variable converges to something, another variable converges to something, then their sum converges to the sum of these somethings. Well, good. Let's see. I know that this converges to e of x squared, this converges to mu squared. Well, their difference, therefore, converges to this difference. And I know that this difference is what? Is sigma squared. Therefore, we showed that the method of moments estimator for variance is consistent, but biased. So what does this mean about biased? Well, the sample size is not large. When the sample size is not large, then it's highly likely that you will miss your target. When the sample size increases, the probability that you will miss your target decreases. Because if n is large, look, we will go back here and compare these two formulas. Look, if n is, let's say, 1 million, so is there going to be a large difference between 1 over 1 million and 1 over 1 million minus 1? Well, the difference is not going to be that large. But if n is 10, then 1 over 10 and 1 over 9 gives you sometimes considerable difference. Well, depending on what you have here. That's an illustration that even though sigma squared hat is biased estimator, but it is consistent because both of them will shrink to the same target, to sigma squared, as n goes to infinity. Yeah, using the same argument, we can show that s squared is also consistent. But now, okay, so from these two estimators, sigma squared hat is biased, s squared is unbiased, both are consistent, still 2-1 in favor of a sample variance. Are you alive there, guys? Are you following?
Almost live.
I know, it's
I
Friday
think I'm
evening.
dead inside.
What? Okay, so the last property that we need to introduce, this property is called efficiency. But before we start this discussion of efficiency, we need to introduce one important concept. This concept is a mean squared error. Well, the introduction was in this lecture that there are many possible parameter estimators. Estimators are random variables. They may have some spread around their mean. So at the moment, until this moment, we spoke only about the target. whether we are shooting exactly in the direction of target or whether we are kind of missing this. So now we will speak about how large is the spread of our possible shots. So they may have some spread around their mean, and we logically want to use such estimators whose sampling distribution is highly concentrated about the true parameter value of theta, right? So we want this possible error to be as small as possible. I guess it's very logical, right? I want to miss from my target by the smallest possible value. How we can measure this error? Well, there is a measure called mean squared error of a point estimator theta hat. So what is this mean squared error? Be careful. We are talking about the probabilistic properties of our estimators. So that's why it's not calculated, and once again, you are never able to calculate this mean squared error from your data. You will be able to calculate the analog of this, the sample analog, and we will do this. But now we need to understand the concept. So the concept is the following. I want to find the expectation of the deviation from my estimator and theta and the population parameter squared. It looks to some extent similar to variance, but it's not actually. We can rewrite this expression slightly differently. We can rewrite this after some operations I decided not to show them here. We can rewrite this as a variance of theta hat. So this is familiar to us. Plus this term. What is this? We introduced this several slides ago. This is a bias. This is the bias of our theta hat. So therefore, this mean squared error consists of two parts. One part is the variance of an estimator. So the estimator is a random variable, and every random variable has a variance. So, and theta hat must also have this variance. Plus, if the estimator is biased, if the estimator is not biased, there is no plus, and mean squared error is equal to this variance, and that's it. But if the estimator is biased, the mean squared error increases by the square of this bias. So that's another reason why we do not want this bias to appear, because with the help of because of the bias, this error increases. And basically, going a little bit ahead, there is another class of estimators. So we know at the moment method of moment estimators and maximum likelihood estimators. So there is also a third class of estimators, which is called mean squared error estimators. And we will introduce them in econometrics. And now we introduce the idea of efficiency. So if we have two unbiased estimators, so no bias there, theta 1 hat and theta 2 hat of the same parameter theta. So in practice, you see that we have two estimators for a population variance. We have method of moments estimator, where we divide by n, and we have a sample variance, where we divide by n minus 1. But okay, method of moments is biased estimator. But at least I hope you understand what we are talking about. So two different rules, how you can shoot in the direction of the same parameter. Well, it's possible that both rules are different, but both unbiased. You will see the example on the exercise session. So both of these estimators have some variances. Variance of theta 1 hat, variance of theta 2 hat. So the efficiency of theta 1 relative to theta 2, we denote this as F, is defined as a ratio, just the ratio of variances. Well, if this ratio is less than 1, then variance of theta 2 is greater than variance of theta 1. And if this ratio is less than 1, it means that theta 1 is more efficient than theta 2 hat because of these variances. So basically, we want to find such an estimator. We want to find such an estimator that has the lowest possible variance. So today, unfortunately, I don't have time to demonstrate you how we can compare these things, but we will start the next lecture with this, and you also will see some examples on the exercise session. So at least for now, you need to understand the concept. And the concept is very simple. We want this spread. So if you will go back to the picture here. So we want this spread around the true population parameter when the estimator is not biased. We want the spread to be as tight as possible. Like this bell must be as tight as possible. In this case, we will call this estimator efficient. The next question is there any limit on this variance? The answer is yes. We will introduce this limit later. But it's not possible to obtain an estimator which has zero variance. It's not possible. There is always some lower bound for this variance. Why? Because an estimator is a random variable, and every random variable must have a variance. So, yeah. What do we know now regarding our blind seeking for the unknown parameter? We must consider several properties. When we establish the rules, how we should behave, how we should act in the search of the unknown parameter, we must act with the following rules. First of all, our estimator must be unbiased, which means what we expect coincides with what we are looking for. Consistency. As the sample size increases, so my guess becomes more and more precise. The deviation from my shot from the target shrinks. It's never zero, but the probability that it will deviate by some small amount tends to be zero. And efficiency. We want such an estimator that produces us the minimum possible variance. Okay, so that's it for today. I mean, from this material. I also have 2 bullet points regarding your next home assignment. So first of all, home assignment number 3 about sampling distributions, which is based on the exercise session number 3, is going to be available tomorrow. You will have similar problems to what you had on the exercise session. As usual, you are not restricted to only Python. You may use Excel, but since we are transferring to Python, you are highly recommended to calculate the quantiles and probabilities with the help of Python. I went through your quiz number 2, and I found that some people made mistakes in the calculation of the probability. So probably, what we can do, I can leave you some comments what was wrong with your calculation after the weekend, and you will find, so when you go to review of your quiz, you must be able to find my comments. Basically, I left the solutions there. So how exactly you need to calculate these things. So please pay attention to this, because otherwise, if you will not be able to calculate these quantiles and you will not be able to calculate your probabilities, well, the home assignment is not going to be correct. So please pay attention to the quiz number 2 and pay attention to the suggested solutions of that quiz. Well, and we will keep moving with Python. So there is going to be tutorial number 3 after the weekend and quiz number 3, which are going to be available hopefully on Monday. I plan to introduce you to working with the Excel spreadsheets. So how to upload Excel file and Excel table into Python, how to work with these, and how to apply the familiar functions like calculation of the mean or sample variance, finding the maximum and minimum, and so on. So that's going to be the main point of tutorial number 3. Because as I promised you, we are moving in the direction of working with the real data. That's why this tutorial is essential part. Questions?
No questions.
No.
Nice. Sometimes it's better that you have questions. So, Vladimir, I'm waiting from you for the suggested day and time of your exam retake.
Yes, I think we discussed it and we decided to put it on the Monday, this Monday, 5
Monday,
o'clock.
7th.
Yes. 5 o'clock. Is it